Okay, so now onto some review problems. Some of these are pretty tricky, but I'm going to go over them with you. And if you want to start, if you're seeing these as pretty easy, or if you feel really confident in these, you can start moving ahead, and then you can start checking yourself as I catch up with you. Okay. Taylor asks, is it possible to do chapter 6 prior to reviews? Good question. So these review problems are for the chapters I just covered. What I'm going to do is I'm going to go through these reviews, solidify the material that we just covered, and then I'm going to do hemiketals, acetals, whatever, and that has its own little review section in it as well. So we'll get practice doing both, but I want that ketal and acetal section right at the end, so it's fresh in your mind. It's going to be the newer thing that I wasn't able to cover. So it's a good suggestion, but I'm going to finish with the ketal acetal section. So number 1, use a mechanism to explain the major product. So I'm going to give you a couple seconds to think about this one, because I think that's important, because on the test you're not going to have some guy, you know, in his house telling you how to do it. So give it a little try. We'll see where we get with it. Okay, I think a few of you have at least looked at it, but the most important thing to recognize right now is we've got HBr, and a lot of us want to be like, oh, HBr, we're going to do a halogenation, hydrohalogenation right there. We're going to add hydrogen here and bromide here, but that assumes that the only thing hanging out would be HBr in water, right? So HBr in water, yeah, you're going to do your hydrohalogenation thing. Here we have methanol. And we notice in our product that methanol is actually going to be in the product. So maybe methanol is going to be acting as a base here instead of bromide. So let's look at what could happen. So we know we're probably grabbing proton here from our acid. I'm going to start getting in the habit of drawing these equilibrium symbols. So where's our carbocation going to be? It's going to be on the most stable one. It's going to be next to that oxygen. That oxygen has some electrons. It can help stabilize it. That was in the resonance chapter, so I won't go over that again. So we end up with the carbocation right there. And now we have to wonder, okay, is Br attacking or is methanol attacking? Well, it's pretty clear based upon the product right here that we have methanol attacking. And that's probably going to be kind of a concentration thing. So I'm sure this methanol is just a massive solvent, and we have a lot of it ready. So we have MEOH. It's going to attack right there. We formed an oxonium thing. We have to deprotonate it. We can use Br to deprotonate it. Or we could also use MEOH, the methanol, to deprotonate it. Question is it wrong to have the bromide take a proton from the methanol before it attacks the carbocation? Bromide is not going to be a strong enough base to pull that single proton off of methanol. if methanol has, if it's an oxonium kind of thing, then yeah, bromide can do that, but it's not going to grab a single methanol right off the bat. Remember, hydrobromic acid is a pretty strong base. It's not going to be able to deprotonate it first. Okay, I want to open up a little bit of a poll. Oh, first Carol asked, I approached this question doing a hydrohalogenation first and an SN2. Would that work also? Let's see, so we get a bromide right here. Is that what you're thinking? And then an SN2. So an SN2 requires a strong base. Remember, methanol is not a very strong base. So I don't think you could pull off the SN2 with this one. You're going to have to go through like an SN1, or you're going to have to form a really good leaving group. Sorry, a really good stable carbocation. So that's a really good question. I want to open up a poll right here just to see where you guys are. Was that a hard problem? Great. That's kind of where I wanted that problem to be. That is like an average problem right there. So it has a little tricky bit to it, you know, having to deal with methanol attacking right there at the carbocation involves some previous knowledge. So great. So we can ask the question now, why does the following product not form? And I covered this earlier in previous chapters, so I don't want to belabor this too much. But resonance stabilized, this whole thing about this guy forming and not that guy. I think you guys should have been able to piece that one together. You always look towards the resonance stabilization of the carbocation, and sometimes that's done by having an by having a group nearby that can donate electrons, right? That was kind of a tricky explanation for you. Talk to me, email me, go through it again, go to your textbook, but that should be something that you're familiar with by now. Okay, 2, provide a mechanism for the following transformations. We've got bromine and we've got a formic acid. So I'll let you think about that one for like 30 seconds. Try to piece together how you're going to get a single bromide attacking or getting added to something that's alpha to a carbonyl. So just to push you guys in the right directions, I want to make the point that we need to somehow create some electron density in this area in order to grab a bromide, right? So that's what you should be thinking. So it's up to you to figure out how the heck you're going to get some electron density right there to make that attack. All right, I'm going to jump in. If you're working through it already, nicely done. If not, I'm going to see if I can catch up to where you are. So yeah, Jamal, we'll jump right into that. Yep, you got it right. So what's going to happen, I'll erase all this stuff right here. We've got a proton right here. And remember, if we're near a carbonyl, we have an inductive effect, right? So this proton is will end up not necessarily pop right off, but it is labile. It can be grabbed. So what we're going to do is we're going to activate carbonyl. So the very first thing you do, remember, when you see that carbonyl, you should be like, I want to make that nice and electrophilic at the carbon. So essentially, this is going to grab proton off of formic acid. Nice. You have just activated the carbonyl. And now you've made it so that this alpha proton can actually be removed, and you can add some electrons into this cycloketone group. So this is one that you definitely need to have the equilibrium arrows on, because this is like a keto-enol tautomerization. I'm sure you guys covered that a bit, but those are happening back and forth. All right, so we have a formate. We have got that conjugate base. It's one to pull off that slightly acidic alpha proton, that thing that next to the inductive carbonyl. Great. Now we have some electrons that can move around. And remember, with keto-enol tautomerizations, you can actually turn this carbon right here, these guys, into you can make them attack something. So fortunately, we have something to attack. We've got bromine. What will happen here, these electrons will come down the oxygen. This is our keto-enol attack. And now you might be asking, okay, we've got that extra proton hanging on that ketone. We got this oxonium thing. Let's remove that. Remember, we still have one free electron-rich bromide that we can attack with. Excellent. So that gets you through that mechanism. I'm going to give out that same poll one more time. Was that a hard problem? Yeah. Okay, good. Yes. Good. You guys are getting challenged a bit. I agree. That is a difficult problem. That's going to be something that you might see on the tests. You have to really make some difficult decisions. You have to remember some ketol-enol tautomerization that you covered, in which that carbonyl can kind of swing electrons up and down. But go through that problem again if you need, and really solidify this concept. That's going to appear again and again, where you pull off a proton, throw some electrons on an activated carbonyl, and then you just swing them back. And really, this happens in biochemistry all the time, that I just call it the swing up and swing down. You swing electrons up, and you can swing electrons down. Oops, sorry. Swing electrons up, and you can swing electrons down. That happens all the time with carbonyls. Electrons up, electrons down. It just serves as a way of moving things around and forcing reactions to occur. And we see something very powerful here. We see that we're actually swinging those electrons down to make it so that this double bonded carbon, these guys right here, can act as a nucleophile. Really important concept. I want you to go over that until you feel like you could do that pretty well. Okay, going to move on to the next one. Ooh, we've got a ring, and we've got HCl, and we've got water, catalytic HCl, I should say. So just enough catalytic HCl to turn that H2O into H3O plus, right? Okay, so I'm just going to start jumping into this. So we've got our hydronium thing hanging around. And in the end, we need to turn this into this. Good way to do that is to make sure that this methoxide leaves somehow. How do we make a methoxide leave? It's the same thing as getting an alcohol to leave. You got to protonate it. If you want something with an oxygen to leave that normally shouldn't leave, you got to protonate that thing. Nice. So that looks like a decent leaving group. And we could say like maybe it'll pop off by itself, but fortunately we have an oxygen right here that's going to help encourage that leaving group to leave. Right, we form our methanol. And we have to go back to what that product is asking of us. We need to somehow get an OH on there. Well, we know what has a good OH in this. We've got water. So water can attack, put those electrons back on here. Now this guy could fall off, right? It seems like a good leaving group, and you'd be like, oh, why doesn't this just kind of kick it off again? Well, then we'd just be going back where we started from, and we wouldn't get any work done. And that does happen. It goes back and forth, and a lot of non-useful reactions happen. But we're asking the question of, well, what could happen? And we have maybe OH2, or maybe some residual chloride or any kind of base hanging around. It's going to pull off that proton, and we're going to end up with our product. And I want to add one note. That could have attacked from either the top or the bottom right here. Okay, we got a question from Brenda. Why doesn't the oxygen take hydrogen from HCl and the water comes in to attack the central carbon and then methoxide falls off? So let me make sure I'm getting what you're saying straight. Oxygen takes the, so guessing you mean you're talking about this oxygen? Okay, so I'll ask for some clarification from Brenda, but Carol's asking, why couldn't you have just made a carbocation instead of bringing the electrons of oxygen down? So you're asking, why doesn't this just leave? So it can, but you're facilitating it by having the oxygen nearby. So you're just kind of pushing it. It's like someone giving a little bit of a push to a good leaving group instead of just relying on it to pop off. But you're right. You've got a good leaving group. It could fall off, but now you just promoted it. Great. Thanks, Carol. If I didn't get to your question, like I keep saying, talk to me afterwards, and we'll make sure everything's settled for you. All right. This is a beast of a question. This is like the one that separates kids from adults here. This is a question that I received on my midterm too. What was it, like 8 years ago? I don't know. I'm getting old. I forget how long it was. But they give you acetylene, and then you have to make this giant complex. And that seems very mean, right? But the first thing I want you to do in these problems is start looking at your carbons, making sure everything kind of makes sense. So essentially, we have a 2-carbon starting material, and we have a 6-carbon product. So we kind of know what things we have to make. We have to make something that could be attacked by maybe an acetylene molecule. We have maybe another acetylene molecule that was reduced right there. This might have been an acetylene that was reduced plus hydrated. And this one's pretty simple. This could have just been acetylene that was reduced. Okay, cool. We've kind of identified where the parts came from, but how do we stick this all together? And this is a very, very important concept that I hope you all just pick up your ears for a second. Remember that you can form this guy using pretty good base. All right? This is glue in the chemistry world. You are essentially forming carbon-carbon bonds using this acetylate glue. This is massively important to remember for synthesis problems because this is how it gets done. It's very difficult to use this guy or this guy. It's way easier to start with acetylene, and it forms a much more stable base, so you can actually deprotonate it, and then you can start gluing carbons together. Okay? So let's start by forming the thing in the center. How are we going to go about that? Well, we don't need any glue yet. We're not going to be gluing any carbons together. So how about we just start off by, I don't know, reducing this and then adding an alcohol. Right? So what can we use to reduce it? We can use our pal H2PDC with Lindlars, because if we don't use Lindlars, we'll just get an alkane, and that's pretty boring. We don't have to worry too much about stereochemistry right here because there's nothing interesting on the side. There's no important stereocenters, no cis trans here. It's all just hydrogens on the end. And then if we use acid catalyzed hydration, we can get an alcohol. And you might think like, hey, I made the alcohol. All right, now I just got to jam a bunch of carbons on there. But this isn't a really good site for a nucleophile to attack. And that's important for these problems because you need to make it so that something can actually go in, some glue can actually adhere to that molecule. The way we're going to do that is we're going to use PCC to turn that into a carbonyl. Nice. Remember carbonyls? They've got that electrophilic carbon right there. We can actually now start gluing pieces in there. So maybe this is the first one we use. Here's the second one. We're going to form our glue. It's a good base. And then now we can actually piece these together. I'm going to write workup, so that's going to be how we get that extra proton on there, and that's perfectly acceptable. Saying that you throw some acid in there, that's going to protonate things. Okay. Right? So just to make sure we're clear, those are those carbons, 1, 2, and these are these 2 carbons, 1, 2. Nice. So let's start reducing that. And we can go all the way here. Okay, so what have we made so far? We've made this portion. We need to find a way to glue another acetylene on. Well, we're going to use that same exact trick we did earlier because we want to attack right here. We want to add another section of carbons right there. We need to glue something. So let's use PCC again. Nice, we made a good thing to glue. Now we've already shown how we're going to make acetylene, so we don't have to do that again. Or acetylene acetate thing. Right? So what's the next step? Once we formed this guy. We need to do one final reduction. Remember up here, we have this trans alkene. Well, we remember how to make trans alkenes, right? What are we going to do? We're going to get some metal, like lithium, and we're going to throw that in ammonia. There we go. So I did the flip of the molecule, but the same thing. If you followed all of those steps, or if you were able to predict what I was about to do, you are in great shape for doing synthesis problems. This is a hard problem that I think only 25% of the class was able to even get like halfway through when I took this midterm. I put it on there because you guys need to be challenged and you need to see what's out there. So if you can kind of master that and you understand the gluing of carbons and the use of PCC to make alcohols activated and making carbonyls, you're doing great. So I'm not even going to open the polls because I'm pretty positive most of you guys are going to say that was a very hard problem. But that's something I want you to think about. And there was some people mentioned, Keith, you weren't doing enough hard problems. And I was like, well, I'm getting to them. I'm getting to the really big ones that are going to show you how all this information comes together and the level of difficulty that you might expect on a very difficult exam question.